Cool. Well, welcome everyone to this week's AI theory seminar, and actually the first one that's officially held with Fields. Um, and that we're deciding the name, so it's either we can either the current name or mathematical AI seminar. That's the Fields name. We'll figure out which one sounds better. um, Anyways, okay, so that's it. Today we have actually that was a great idea to have like a local speaker, and specifically we have one of like a more recent PhD students at Masters, so like Dennis. I can never say your last name, but no one can say my first name, so it's fair. Zvigelsky. Okay, so Dennis
That's
is
pretty
doing.
good. Yeah.
Thanks, I did practice. So so Dennis is doing his PhD with me and with Brad Hart. So it's jointly in, I guess the topics are like related at the moment. We'll say it's related to AI reasoning, but so it's like mathematical theory of AI slash model theory. So it's a pretty cool new intersectional area, which makes a lot of sense for the topic. And he'll be speaking about, I guess, I guess your first paper that's like related to the PhD we were trained on, which is the following. So quantifying AI reasoning via systematic neural network representations of algorithms. So back to you, Dennis.
Great. Okay. Thank you so much, Anastasi. That was a wonderful introduction and pleasure to be here. Okay. Yeah. So let's dive into it. So, like Anastasi said, this is joint work with my two co-supervisors, Anastasi and Brad. We're from McMaster, and this is joint work with the Vector Institute. Okay. Oh, here we go. Okay. So, here's basically the goal of what we wanted to accomplish. So the overarching goal is we want to provide a rigorous framework for AI reasoning. And essentially, when we typically think of a neural network, we think of it sort of as a black box. So what we want to do is we want to go in to this black box, we want to peer in, and we want to characterize the internal chain of thought that exists inside. And when we do this, we want to do this without sacrificing various approximation theoretic guarantees. And furthermore, we actually want to provide them. We want to explicitly demonstrate them. And alongside those kinds of results, we also want to get new guarantees for the expressive power of neural networks. And we'll see exactly how all of this plays out shortly. Okay, so in terms of the main contributions, so the first main one, and the sort of credo that we're going with here, is that we married approximation and complexity theory. And how did we do this? We basically grounded chain of thought reasoning in terms of circuit complexity. So what was the first theorem? So this appears as like theorem one in the paper, is that if F is computable up to precision Q, and exactly what we mean by precision Q is going to be mentioned later, but um, yeah, and with an underlying directed acyclic graph script G with n gates in some set G to be specified later, then there's essentially this neural network F prime computing F such that the following holds. So the first condition is essentially that up to precision Q, F and F prime are equivalent. In terms of the size of the resulting neural network F prime, and sort of scales with n, the number of gates in this in this deck G. And the structure of the neural network is actually similar to the computational graph structure of G. Right. And the second main contribution is as follows. So we sort of prove like a digital analog of the Kolmogorov-Arnold representation theorem. Excuse me. So essentially, for all functions f that go from this sort of discrete uh, reals with up to a certain precision q, r, d, q, and again, this is all going to be specified later as to exactly what we mean, then there exists this neural network f prime such that they're equivalent. But in this case, not only are they equivalent up to precision q, they're actually exactly the same in terms of extensionality. And I'll mention exactly what extensionality means later too. Um, in terms of the size is pretty large in terms of the width and the number of non-zero parameters. And the basic reason for this is due to the construction, which basically involves placing scaled spikes along each of the points x in the input space. And because your input is d-dimensional, so you sort of have this cursive dimensionality that such that when you construct this sort of spiky surface as pictured below over here, um, it scales with these. So really, it's not necessarily too efficient, but nevertheless, you actually get an exact, representation of your function f with your neural network f prime. Okay, so I mentioned this word extensional, and I want to sort of now give over the vibe of what we want to capture formally when we talk about reasoning. So here's the sort of qualitative explanation. So reasoning is sort of extensional and intentional. Extensional basically means, sort of from the approximation theoretic perspective, that we want to capture the external output behavior of our function f. So what that basically means is that given an input, let's say x, then your output is guaranteed to be y. So the input-output relationship is maintained. So you don't necessarily care how you computed it, but you just care that sort of at the end result is some value y. Now, from the complexity theoretic perspective, you actually care about the sort of chain of thought and internal structure of the function f. And in this case, that's sort of speaking to the intentional definition or structure of f. So it's not just enough to sort of get the input-output relationship correct. You actually care as to how you arrived at the answer. So here's what we basically do then in the context of our neural network representation. So basically, when you're given a neural network, typically you just have this sort of black box. So we want to reject this kind of model. We want to peer inside, and we basically want to see the logical gate structure that's contained therein. And not only are we concerned about, let's say, logical gates like and or like an existential quantifier, but we're also caring about arithmetic operations or analytic gates, tropical gates, and so on. So we basically want to look at the sort of circuit structure that's contained therein. And then we want to sort of provide neural network corresponding representations of these gates, which basically perform the exact same function. So extensionally, they're going to be the same, but then when you sort of compose all of the neural networks together, you sort of have like a little and sitting inside, or like a little, tropical min-max sitting inside your neural network. And as it comes together, right, you sort of have a neural network that has the same extensional structure, but also the intentional circuit reasoning contained inside that matches the circuit structure that you're modeling. Okay, so in terms of how we're actually going to accomplish this, this is done by way of surgery. So before we get there, and exactly what I mean by surgery, we need some notation. So letting D be a directed acyclic graph, we can partition D's nodes in the following way. So the input nodes are essentially consisting of all the vertices that have no parents. The output nodes consist of all the vertices that have no children, and then the computational nodes is basically everything else. So the vertices that have children and parents. Now G here is essentially going to be this big union of all the functions from Rn to R, and we also require that the identity is a member of G. Okay, great. So now we can give the definition of an elementary G circuit, which is as follows. So it's essentially this triple A with VEG. So VE is a DAG, and basically it has D inputs, little d inputs and big D outputs. The vertices are essentially labeled by natural numbers, which would be convenient if you want to give like a kind of ordering. And then the gates are basically given by gates at each vertex V. And all of them are sort of these like G gates as specified by like math DDG above. And we require the following compatibility conditions to be met. So basically for all input and output vertices and all inputs X, you essentially want that the gates at those input and output vertices to act as the identity. So the basic idea there is that no computation is going on. Sort of like you're fed inputs and then you don't really compute with it. You're going to feed it onto the computational nodes and they're going to do the computational processing. Now, with regards to the computational nodes, so given that it's a computational node, so it has a parent or has a set of parents, so you basically want there to be this compatibility, right? So the images of all of the gates at those parent vertices, right? That has to be a subset of the domain going into the gate at vertex V. So you sort of can feed in the outputs of the gates at each parent vertex into the gate at vertex V, which is just a given computational node. Okay, and basically all of this gives you a definition of the function that a given circuit computes. So basically, given an input X and RD, so you can sort of order the input vertices of the given graph, of the direct acyclic graph, and then you essentially set X V1 through VD to be literally the input, the d-dimensional input of X. Then for all computational vertices with given parents, you essentially define the sort of X value at that that vertex to be the output of the gate at that vertex on to the inputs that it gets from the parent vertices. And then finally, in terms of the output, you essentially now, or given the output vertices, you can now essentially define the function that it computes, which is just the sort of x coordinates or the x values at each of those output vertices. And basically, the thing to stress here is that this is very much an intentional definition, right? So yes, we're computing a function, but we really do care as to how we computed it, right? We do have an internal structure, and there's a corresponding, gate for each vertex. Right. Okay, so now we're ready to define surgery at a node. So basically, given two G circuits A and B, and basically B has this output vertex V out. You let V be a computational node, and if there exists, you sort of have this rewiring map that what it's going to do is it's going to try to take out the vertex V, or really what the surgery at a node, at a bird's eye view is doing is it's basically taking out this vertex V and replacing it with the circuit B, and essentially you want to make sure that there's like a compatibility condition, which is why you want surjectivity. Okay, so the B surgery of A at V via this rewiring map F is going to be a G circuit and denoted as follows. And here's how we define it. So step one, basically what we do is we remove V. Then in step two, what we do is we first detach all of the edges that are associated with V. Then we add all the edges that are associated with B. We're going to add in the inputs associated with B, right? The edges that are associated with B's inputs, right? So given, parent vertex U for V, then we essentially want to add the corresponding edge according to the rewiring map. And then we also add B's outputs, sort of basically connecting um, adding the sort of, output edges from V. Okay, and then at the end, we essentially look at the corresponding gates that are in this new G circuit, and essentially just going to be the gates in B with the gates in A, and we essentially took out the gate at V. And then basically we term such a surgery flawless if F is a bijection. So you sort of have this, really nice mapping between the parent vertices and the inputs of V, of B. Okay. And now surgery in general, the basic idea of surgery in general is that you sort of have like a repeated surgery at a node. And we essentially term the entire surgery flawless if at each time that you basically want to replace a given vertex in a graph with the corresponding circuit, it's going to be flawless. And then if you've replaced all of the vertices in your G circuit with another corresponding circuit, then we call the entire operation to be a completely flawless surgery. Now, I mentioned before that we're doing all of this in the context of a discrete grid. So here's basically the definition of how this works. So if you're given a Q, a value Q that's going to be a positive integer, then essentially you define the reals up to precision Q to be sort of the reals that can be represented by a binary string with the following representation. So sort of imagine like one bit reserved for sign. So like if it's positive or negative, then you're going to have Q plus one bits for basically powers of Q from 0 to Q plus one. So like 2 to the 0, 2 to the 1, all the way up to the 2 to the Q plus one. And then you sort of have the same thing going the other way for the negative powers of Q going from -1 to -Q. So all of those numbers that could be represented in such a way, that's going to be our Q. Right. And then basically given any X and Y that are members of our Q, then we essentially defined addition and multiplication to be, mod 2q plus 1. So you essentially take the representations, you add them, and then take it mod 2 to the q plus 1. Okay, so um, what we're essentially now going to move towards is to try to essentially prove theorem one, or trying to understand how we prove theorem one. And we do this by essentially finding neural network representations of different gates. And then if we're able to do that, then we can essentially perform a surgery, take out all of the different, you say like an AND gate or some kind of tropical gate, and replace it with the corresponding neural network representation. And then if you sort of have a completely flawless surgery, then we are going to end up with a neural network that represents the given function and has the computational structure. So towards this, let's start off with some logical gates. So in this case, letting A and B be inputs, binary, to be binary strings essentially, size B. So let's look at this first neural network over here, phi and. So in this case, essentially what we're doing, right, is we're taking A plus B minus 1, and that will compute, A and B. NAND is essentially the same, but you're doing 1 minus the previous result. Equals a little bit more intricate, but it's not too bad, because basically what ends up happening is that if A and B are equal, then ReLU of A minus B and B minus A, they're going to be the same. And so that whole, little subclause there is going to evaluate to 0, and then taking ReLU of 0 gives you 0, and then 1 minus 0, 0. ReLU of all of that is going to give you 1. And so the basic idea is that, phi equal is going to be 1 if and only if A and B are actually equal. And so here's basically a summary with different logical gates that we have here. So we can basically represent NAND, and, ORs, or implication not. We can also do propositional logic, although the complexity there is a little bit different than what we have with the predicate logic or logical gates above. But the nice thing is that you sort of have this linear dependence and with a number of parameters for the logical gates. So that's pretty cool. Okay, now moving on to analytic gates. What we basically have is that if we let X be a real number, Q be a positive integer, A and C be members of our Q, then we have the following. So you sort of have this constant map. So what it essentially will do is that it will set, your its output is essentially some constant in our queue. And the way that it accounts for this, right, is that, well, depending on whether C is positive or negative, the way that we've set it up is essentially it accounts for this. In terms of the analytic function, that essentially is like an indicator whether some X is in the interval A infinity, right? So the idea is that if X is going to be greater than A, then the inside of this inner ReLU is going to be negative, so then it evaluates to 0, so then the output's 1, and then the 2q plus 1 is essentially going to be a threshold that scales relative to the precision that we have up to precision q. And then basically it's the same sort of idea when it comes to the gate below, or the neural network corresponding to the analytic gate for the indicator negative infinity to A below. Right, and then here's basically a summary of some analytic and tropical gates, and we'll actually need a tropical gate going forward in terms of one of the applications of theorem one. And finally, we sort of have these kinds of bit manipulator and modular arithmetic gates. There's actually more. There are more gates in the paper. It's just, didn't want to list all of them, but this is just a nice sampling of what's possible over here. The idea is that the bit encoder will take a real number or up to precision q, right, a guy in our queue, and then transform it into its equivalent binary string representation. And the bit decoder is essentially the inverse operation. Left shift just shifts the binary string, right shift also shifts the binary string to the right, and then modular addition and multiplication performs extensionally as was defined previously. Okay, so now we're ready to dive in to the first big theorem, and here's basically how it is stated formally. So if we let A be a G circuit with the gates, or with gates as we presented just previously, then there's a complete flawless surgery of A, where for each vertex in the computational nodes of A. BV is the ReLU MLP, whose depth and width is bounded according to its gate, and FB is the ReLU feedforward neural network. So this is basically what's going on here is essentially what we were describing before, where we really do systematically replace each gate in A with its corresponding neural network from the table. And then essentially, if we do a complete flawless surgery, then we end up with a neural network that has some really nice properties. So the first thing is that this sort of theorem formalizes the correspondence between algorithmic time complexity, neural network space complexity. Why? Well, because the algorithmic time complexity is essentially determined by the computational structure in the G circuit. And what we're essentially doing is for each sort of computation that we're performing, we're replacing it, sorry, with a corresponding neural network. And that's why there's sort of this really cool dependency or correspondence between the two, which actually kind of formalizes the folklore result that states exactly as such. And the other really nice thing about this theorem is that it actually gives us existence guarantees in terms of like what neural networks are capable of solving. And we can actually even get explicit width, depth, and parameter bounds as well. So that's what we're going to focus on next. So here's one of the corollaries of the theorem. So what we're essentially able to do is we're able to represent generic Boolean functions. So let B be a positive integer. Then there is an absolute constant C, such that for every Boolean function f, there exists a ReLU feedforward network with at most this many number of non-zero parameters. In particular, it's O of 2 to the B. So how does this work? So here's theorem 1 in action. It's quite cool. So here's what you do. You essentially see if there's a result that already exists that basically gives you a particular G circuit. So in this case, Loshkin in 1996 states that there is a C greater than 0 with the Boolean G circuit A with gates in and or in not, such that the number of computational nodes in this G circuit is given by K, which is the following, number. And essentially, the function that it computes is exactly our Boolean function f. And essentially, just applying our theorem, we can do a surgery, and in the worst case, I think OR had 6b non-zero parameters. So if you just multiply k by 6b, you can essentially see that there is a ReLU MLP with at most k times 6b non-zero parameters that will implement this this function. Okay, another really cool corollary is solving the all shortest paths problem. So essentially, the idea is that you're given a graph and you basically want to compute a matrix, or just really even without thinking necessarily about a matrix, just you want to see the shortest distance between each pair of vertices in your graph. And this is essentially given as a matrix, right? So given G as the graph, you can define K to be um, the number that essentially corresponds to the number of edges in the complete graph with few vertices. Then you essentially have a ReLU feedforward neural network with O of the cubed non-zero parameters that basically solves the all shortest paths problem. And this is for any, input weights in RK Q. So how does this work? Again, really cool. So what you do is you essentially see, oh, okay, an example 1.8 in a result in the textbook by Yukna, there's essentially there's an existence of this G circuit that is of size O of V cubed, that has gates in min and plus that solves the problem. So by theorem 1, you essentially know that you can perform this complete flawless surgery, and then you get your ReLU MLP that has O of V cubed non-zero parameters that solves the all shortest paths problem. Okay, and now moving on to theorem 2. So the basic idea behind theorem 2 is that you can actually, well, as we said before, it's sort of like a digital analog of the Kolmogorov-Arnold representation theorem. So what we're going to do is essentially we're going to construct a spiky surface that corresponds to a given function on RQ, and we actually get the function exactly. So what we essentially say is that there exists, given D, Q, and N1, that are sufficiently defined or defined sufficiently. you get this universal encoder ReLU MLP phi encoder of depth 4 with 2 and 1 and less than 2 and 1 non-zero parameters, such that for each function f that is given on these reals up to precision q, there exists this matrix beta f with entries in well, the function values on each input x, satisfying that for all x, beta f time transpose times phi enc is going to give our function. So essentially the idea is that phi enc will pick out and give you a one-hot vector essentially on the particular entry that corresponds to the point x, and then beta f is going to scale that particular value um, according to the function's value at that point. And that's why you sort of get this nice spiky surface. And the thing to note is that, again, the width is pretty large, right? And same thing with the number of non-zero parameters, because you sort of have to account for the worst case in this construction. Okay, now moving on to the last topic of this talk, we're going to be talking about notions of G computability. So we say that a function f is G computable if there exists a sequence of G circuits, AQ, such that AQ is of size on the order of rho of Q, and where rho is the rate function, and the function that AQ computes satisfies the following bound. So essentially, it's bounded by some modulus of continuity, and here pi is this projection of the input x into RDQ. And so basically the distance sort of, or the norm between these two values, right? The function that AQ computes on this projected x and f of x is going to get increasingly smaller as Q increases because of the monotonicity of the modulus of continuity. And we essentially denote the set of all such G computable functions by this notation over here with G omega rho, and basically saying that it's from RD to R little d to R capital D. Okay, so we can actually prove a nice little lemma that essentially is going to characterize the kinds of errors that we're going to see when it comes to computing with these circuits. So here's what we got. So we'll define FQ bar to essentially be the F is going to be fed in the input with the projection of some input X into RD, and then we sort of take the output of that and project it again back into sorry, I should have said RQ previously, and also into R capital DQ afterwards. So it's essentially F as it exists in this sort of RDQ space. And essentially for any G circuit A that computes this function that the circuit A computes and any input X, so you sort of have this bound on this distance between, or this norm between f of x and the function that A computes at this projected x. So what are the two different bounds? It's important to note that if there's discretization error and there's a computation error. Discretization error, right, comes from the fact that you are discretizing your input x, and essentially it's going to be up to some precision q. And the compute error is essentially what happens when you look at the function that A computes, and what is the difference between that and the actual sort of projected version of f. So what's the difference between those two? So there are two sort of categories or classes of errors here. And the way that you prove this bound is essentially just through a little bit of triangle inequality. And that's that. So now corollary of this result is as follows. So if you have f be a uniformly continuous function with a modulus of continuity omega, then f is actually in this class of G computable functions with this sort of particular row. And what we can essentially say is that, in other words, for every q, there is the ReLU neural network AQ, such that the function that AQ computes is going to be of a particular size, and it satisfies this bound. And in particular, the compute error is going to be 0. So how do we show this result? Well, by the previous lemma, we essentially get the like a nice bound on the left-hand side of the inequality. And then because of theorem two, right, that actually states that there's a particular size on the circuit that we can, or on the function that we can fix beforehand, right? 2 to the d plus dq satisfies that size. And then we actually can get zero computational error um, in terms of representing that function. So actually that whole computational error will drop down to zero. And that essentially means that this f is going to be um, G computable with these parameters. Okay, so basically, to sum up what we've done, so we gave a rigorous framework that characterizes reasoning in the context of ReLU neural networks. Theorem one, the first theorem that we sort of saw, provides a way to transform a G circuit into a ReLU neural network by way of circuit surgery. And we saw corollaries of the theorem, which gave us new expressivity results. Theorem two gives a more powerful approximation theorem in that it provides an exactly equivalent ReLU neural network when given a large enough precision. And finally, we gave a notion of G computability and showed that uniformly continuous functions are G computable. In terms of next steps, so we would like to investigate G computability in the context of non-Euclidean inputs and outputs. So that sort of corresponds to the geometric deep learning literature, and then also the infinite dimensional case, which sort of corresponds to the operator learning literature. So that's that. So thank you everybody for listening. And yeah, any questions are welcome at this point.
Thanks a lot. It's a great talk. Yeah, also it's been fun to be the first speaker that are transitioning over to fields. Are there any questions in the audience? I personally don't have any questions. I guess not. Oh yeah, Julio? Oh, I think you're muted if you want. Julio, I think you have do you have a question? Okay, I guess not.
Oh,
Okay.
there we go. There we go.
Oh, nice. Okay.
Finally, finally, I managed. It wasn't responding. Yes. Just very quickly, I'm on my phone. I couldn't log in on my computer because of some issues. So I'm on my phone, and I see there's a QR code to the paper,
Mhm.
but I can't get it. Is there any way you can? Um, is there
I
any way
could
you
sit
can?
in the chat.
Yeah,
How about
can you
that?
Yeah.
please? Yeah. Okay,
So,
that'd
Yeah,
be
yeah,
great.
yeah, 100%. Give me a second.
Okay.
Yeah.
I mean, I'll be honest, I didn't understand a lot of it, so I want to take a look at it tonight or this weekend to just
cool.
go over it again.
Yeah,
I just
you could
sent
also feel. Oh, yeah,
yeah.
sorry.
I just sent the link. All right. I beat you to
Yeah.
it.
Okay.
Oh, you sent it? Okay, yeah,
Yeah.
you're
You
faster
did?
than
Okay.
me.
There it is. There it is. I see it now. Okay.
Um,
Okay. Thank you.
cool. Yeah, thanks.
Yeah, and feel free to message me if you have any questions about the paper. So, like, my email should be given there on the paper. Yeah,
Okay. All right.
I'll
I'll
be
probably
happy
have a
to
lot of
respond.
questions, but um, it's been a long time since I looked at this type of math. But I'll try and at least absorb some of it. But it was a very interesting talk. Thank you.
Thank you. Yeah, I appreciate that.
Maybe I have one question without um, giving away too much, you know? Yeah, what would you say is like yeah, I don't know, some related thoughts or things like this, you know, beyond the paper. Like, what would you say is an interesting question next? Maybe not something that we're necessarily thinking about, but if someone else had to think about something that we're like, what's another question that we're not thinking about? That's interesting. That's
Oh,
the problem.
that we're not
This is
already
like
thinking about.
supervisor question.
That we're not already thinking about. I mean, technically, we raised this question before, which is sort of thinking about the reverse case that you sort of have
Hmm.
like an arbitrary given neural network, and then you need to find it sort of a condition where you can decompose the given function into different gates or some kind of other logical structure, rather than sort of assuming that it exists a priori.
Yeah.
That would be pretty cool as well. So you don't necessarily have to generalize to the non-Euclidean case, but you can just sort of focus even on this sort of system that we've set up if there's anything possible to, if it's possible to sort of look the other way. Um, and then I guess you can also like in terms of my own research, right? Like there's also the continuous analog. So um, trying to look at uh, classifying circuits in the continuous setting, and then essentially trying to see what kinds of reasoning um, we can have over there. So if we sort of try to impose the same architecture in terms of
Mm.
the circuit structure, then what would that look like when we're computing with continuous gates and so on?
That makes sense.
So that would also be cool.
Maybe I have like a okay, so like this to summarize one thing. Yeah, I also agree. I think the inverse problem is extreme. Since you have a bit of time, you can just like quickly say, yeah, I think the inverse problem is something very interesting. Like just to say to whoever watches this video, yeah, we're very interested. You have an idea that'd be great. We're not really thinking about this right now, but we're super curious. Like right, because we're going kind of the forward problem. But maybe one question for you, which I think I have an answer to, but I mean
Okay.
one could prove it. I don't know if it's yeah. So there's a lot of work on, say, other architectures. Like, for example, right now, transformers are hot. Like a few years ago, GNs were hot or whatever. Before that, CNNs were hot. And there's always some new architecture, right? But the NLP is simple to analyze, at this point, you know. So I guess one question is like, do you expect that there's any, um, like, unless it's like something some super different architecture that we don't know about yet, do you think that all these things, like any architecture, would have like similar complexity guarantees? In other words, if we're looking at like this like circuit reproduction or emulation lens, like there should be relatively no difference between any like universal kind of model. Like, do you think this like this is
Oh,
what I think, but do you agree with this? It is my intuition. So what's your intuition,
well, my intuition is that you sort of have to have the right parts moving together. So if you're able to have the systematic circuit representation and you are able to come up with sort of mini versions of gates in your given architecture, then the results should hold
Yeah.
because it's sort of, yeah, yeah, if that makes sense.
Yeah, it does, I guess. Yeah, so maybe I just say one comment on this.
Yeah.
I think to me, like I think one thing that like I think is really interesting with this research, I mean there's a lot of things, but I think like I think one conclusion that's somewhat implicit is that I think yeah, I think the research also shows that there in some sense most of the models, like most models given like I say yeah, I think most of the machine learning models you can probably like are which are universal, like deep learning models, not like shallow ones. You should be able to construct a similar proof, I imagine. So I imagine that like the advantage of one model over another should be something more subtle than the ability to represent like a general circuit. So like it's sometimes like the like this paper addressed I think one can probably say that the point of the paper was like deep learning models can exactly compute anything a classical algorithm can do. And so maybe the one follow-up question that could be interesting is that, what makes one architecture more suited to a given problem over another? Like, is it some
Mm,
algorithms are slightly better? Like, are some constants better? I don't know. I think those are interesting questions to follow up.
that would be
Anyways,
kind of interesting.
yeah, yeah,
Like
yeah, yeah. Like, like basically the
maybe
question is like inductive bias versus like general power.
yeah, I would say like in terms of the general vibe of what like theorem one is saying, I don't know if there would be any stark difference, but then maybe in terms of like if one particular architecture is better suited at representing like one difficult gate or something like this,
Yeah,
then the number of neurons that are going to be required for that specific gate are going to be less or
yeah.
something like this, right? So yeah, that would
But
be
like
kind of
here's
cool.
a
Hmm.
concrete
Hmm.
example. I mean, maybe to which I think is too much power for a neuron. But if you were to yeah, so the people who are looking remember the gate the complexity of emulation of different gates or simulation if you're talking about TCS, same word, same concept, different word. Um, yeah, like propositional logic was scaling exponentially in the number of bits. So if one had added a gate that was allowed to search over the entire space, like max of, of the grid, which is obviously too powerful. But if you allowed that, then that would be like a very concrete instance of this, like a model which has like a bias towards like specific subclass of problems. Now, if that model is realistic, probably not. But yeah. Anyways,
Right.
okay, we should talk about this later. We'll see each other in person. But thanks everyone
Right.
for coming. And just as an announcement for everyone else, during the talk we were settling this with Fields people. There'll be a different link moving forward. It's going to be a Fields Zoom link, so that's ironed out. And one more piece of information: the seminar is going to be moving to Tuesdays at 3 to 6 p.m. And there is going to be like a room at Fields for that to happen. Sometimes, but personally, I'll probably be here virtually. All right. See you guys next week, and great talk, Dennis.
Thank
Ciao.
you. Take care, everybody. Thanks for coming.
Bye.